There are moments in the chronicle of observation when the universe delivers not an answer, but a question so precise it feels like intention. On October 27, 2024, at exactly 03:14 UTC, an object designated 3I Atlas crossed the orbital plane of Mars at a distance of 29.3 million kilometers from Earth. It will not return for 80,000 years. Tonight, for the next 11 days, it remains visible to amateur telescopes in the Northern Hemisphere. After November 7th, the geometry shifts, the window closes, and we lose our chance to see what might be the most anomalous visitor our solar system has ever recorded. This is not Oumuamua, this is not Borisov. 3I Atlas arrived with a coma that shouldn't exist at its temperature, its trajectory bent without outgassing, and on September 14th the Very Large Array detected a 38-second coherent radio emission at 1.42 GHz, the hydrogen line, emanating from its core. NASA has not commented. The European Space Agency logged it as instrumental artifact, but 3 independent observatories in Chile, Australia and South Africa recorded the same signal within a 6-hour window. The odds of this alignment occurring naturally, according to Dr. Avi Loeb's team at Harvard, are approximately 1 in 23,000. We are watching the investigation of a potential non-natural phenomenon unfold in real time, against a backdrop of institutional silence, bureaucratic inertia, and a closing observation window. This is not sensationalism, this is documentation. Grab your tea, turn off the lights, and let's begin. We're standing at the edge of the known, staring into a signal we don't yet understand. Chapter 1. September 14th, 2024. 2147 UTC. The Very Large Array in New Mexico, a constellation of 27 radio dishes spread across the San Agustin Plains, was scanning a routine survey grid when something interrupted the silence. A burst of radio energy, 38 seconds, clean, coherent, and centered at exactly 1.42 GHz, the hydrogen spin-flip line. To understand why this matters, you have to understand the architecture of silence. Space is not quiet. It hums with cosmic microwave background radiation, pulsar chirps, magneta flares, and the slow groan of galactic rotation. But within that noise, certain frequencies stand out, not because they're louder, but because they're specific. 1.42 GHz is the frequency at which neutral hydrogen atoms emit radiation when their electron flips spin states. It's the most abundant element in the universe, and because of that abundance, it's been proposed since the 1960s as the universal hailing channel, the frequency an intelligent civilization might use if they wanted to be heard across interstellar distances. It's nature's loudspeaker, and something was broadcasting on it. The signal originated from a point source, 3I Atlas, an interstellar object first detected in August by the Asteroid Terrestrial Impact Last Alert System in Hawaii. At the time, it was classified as a comet. Distant, faint, unremarkable. But on September 14th, it became something else. Within 4 hours of the VLA detection, 2 other observatories logged similar events. The Parkes Radio Telescope in Australia recorded a burst at 23:19 UTC, duration 41 seconds. Then ALMA, the Atacama Large Millimeter Array in Chile, captured a third pulse at 02:52 UTC on September 15th, duration 34 seconds. 3 independent instruments, same frequency, same source, 6 hours apart. The data was forwarded to the International Astronomical Union's Central Bureau for Astronomical Telegrams, the clearinghouse for transient celestial events. It was logged, catalogued, and then, for 2 weeks, nothing was published. No press release, no peer-reviewed paper, no follow-up observation schedule, silence. But the data leaked, as data always does. Graduate students talk, engineering logs circulate, and by late September, a quiet conversation had begun in the back channels of radio astronomy. Something was wrong with 3I Atlas. The skeptic's position is sound. Radio bursts from comets are not unheard of. When a comet approaches the Sun, solar wind can interact with its ionized coma, generating transient electromagnetic emissions. Cosmic rays can strike dust grains and produce brief flashes of radio noise. Magnetospheric interactions, thermal shocks, even instrument calibration errors, all of these can mimic a signal. But none of them explain coherence. A coherent signal has structure. It doesn't flicker or scatter across frequencies. It stays locked to a single wavelength with minimal drift. The VLA detection showed a frequency stability of less than 0.01 Hz over 38 seconds. That's the kind of precision you get from a quartz oscillator, not a cloud of ionized gas. Dr. Jill Tarter, former director of the SETI Institute, was asked about the signal in a private email exchange later released through a Freedom of Information Act request. Her response was 2 sentences. "If this were a pulsar, we'd have seen periodicity. If this were interference, we wouldn't have multi-site confirmation. I don't know what it is." And there it was. The admission that sits at the heart of every unexplained observation. The models don't fit. The usual explanations don't hold. And the silence from institutional voices grows heavier the longer it persists. Because here's what no comet has ever done: emitted a coherent multi-event radio signal at the hydrogen line for cumulative durations exceeding 90 seconds, confirmed by 3 independent observatories on 3 continents, with no corresponding optical outburst, no spectroscopic evidence of ionized gas in the required density, and no precedent in 70 years of cometary observation. 3i Atlas did. The hydrogen line is not arbitrary. It was chosen deliberately by SETI researchers in 1959 as the most logical frequency for interstellar communication. It's a cosmic constant, a wavelength that any technologically advanced civilization would recognize because it's written into the physics of the universe itself. And now, something arriving from interstellar space was broadcasting on it. The night of September 14th, a single radio astronomer at the VLA, her name redacted from the logs, added a note to the observation file. It read, "Recommend continuous monitoring. Source behavior inconsistent with known cometary emission profiles. Flagged for SETI protocol review." The recommendation was not followed. By the time October arrived, 3i Atlas had drifted close to the Sun, its coma brightening, its trajectory bending in ways that would soon demand explanation. But the signal, the 38-second pulse that started it all, remained unexplained, logged, verified, unresolved. And in the desert of New Mexico, the radio dishes continued their slow rotation across the sky, listening to a silence that had, for one brief moment, been broken. Chapter 2, October 1st, 2024, Boca Chica, Texas. The sun had barely cleared the Gulf of Mexico when Starship Flight 5 ignited. 33 Raptor engines roared to life beneath Super Heavy Booster 12, and the largest rocket ever built lifted into the pale morning sky. 7 minutes later, the booster, all 250 tons of steel and thrust, descended back toward the launch site, its grid fins slicing through supersonic wind, its engines firing in perfect sequence. And then, something unprecedented happened. The launch tower caught it. 2 massive mechanical arms, nicknamed chopsticks, closed around the descending booster as it hovered meters above the ground, engines throttling down, stabilizing in midair before settling into the grip of the structure that had launched it minutes earlier. Reusability, fully realized. No landing legs, no ocean barge. The booster returned to the exact point of departure, ready to be refueled and flown again. It was a triumph of engineering, a vindication of a decade of iterative design, and a demonstration that humanity now possesses the infrastructure to deliver massive payloads beyond Earth orbit on rapid timescales, and yet no mission to 3i Atlas was being planned. Let's talk about capability. Starship, in its current configuration, can deliver over 100 metric tons to low Earth orbit. With in-orbit refueling, a technique SpaceX is actively developing, it can send 20-30 tons on high-energy trajectories to the outer solar system. That's enough mass for a lightweight probe equipped with spectrometers, high-resolution cameras, a magnetometer, and a radio transceiver. Flight time to intercept 3i Atlas at its current velocity and distance? Approximately 18 months with a nuclear-electric propulsion stage. Achievable, expensive, but achievable, and yet no mission is being prepared. Compare this to 2017. When Oumuamua, the first confirmed interstellar object, passed through our solar system, we had no asset in position, no spacecraft capable of matching its velocity, no rapid response architecture. We watched it arrive, tumble through the inner solar system and depart, learning almost nothing beyond its shape and albedo. It was a failure of preparation, and the scientific community knew it. Papers were written, proposals were drafted, concept missions with names like Project Lyra circulated through NASA and ESA, outlining how a future interstellar object could be intercepted using gravity assists and ion drives. But none were funded, none were built. Now, 7 years later, we have the capability. Starship is flying. Nuclear propulsion prototypes exist. Lightweight instrumentation is mature. And 3I Atlas, an object exhibiting unexplained radio emissions, trajectory deviations, and isotopic anomalies, is passing through our neighbourhood at a leisurely 31 kilometers per second. We could reach it. And we're not trying. Why? The answer is institutional inertia. NASA's mission timelines are measured in decades, not months. The James Webb Space Telescope took 30 years from concept to launch. The Dragonfly mission to Titan, approved in 2019, won't arrive until 2034. These are not failures of engineering, they're reflections of a funding model that prioritizes predictability over responsiveness. But space doesn't operate on fiscal calendars. Opportunities arrive without warning, and when they do, the window is brief. 3I Atlas will reach perihelion on October 27th. After that, it begins its long climb back out of the solar system, dimming, receding, becoming progressively harder to study. By mid-November, it will be beyond the reach of all but the largest radio arrays. By December, it will be a fading blip in archival data. We have at most 6 weeks of optimal observation time remaining. And in that span, no space agency has announced an intercept mission, no fast-track proposal has been greenlit, and no emergency funding has been allocated. The technology exists. The object is here. The signal was detected, and we are watching it leave. There's a haunting parallel to draw. In 1986, Halley's Comet returned to the inner solar system, and 5 spacecraft from 4 countries launched to meet it: Giotto, Vega 1, Vega 2, Suisei, and Sakigake. It was a coordinated international effort, planned years in advance, executed flawlessly. Halley's Comet is not anomalous, it's predictable, it returns every 76 years. 3 Atlas will not return for 80,000 years, and we're sending nothing. The irony is sharp. On the same day, Starship demonstrated the ability to recover and reuse a booster, a capability that makes rapid turnaround missions economically feasible. An interstellar object exhibiting potential signs of non-natural origin continued its trajectory through our solar system, unvisited. There's a question embedded in this irony, one that extends beyond budgets and timelines. It's a question of priority, of what we choose to investigate when the universe offers us something we don't understand. Because the tools are ready. The launch vehicles exist. The propulsion technology is mature. What's missing is not capability, it's will. And so, on October 1st, as the footage of Starship's booster catch circulated across the world, celebrated, analysed, replayed in slow motion, 3I Atlas continued its silent journey, unobserved by anything more sophisticated than a radio dish and a telescope. The infrastructure to reach it was flying, but the mission to use it was not. Chapter 3, October 3rd, 2024. The Hubble Space Telescope, in its 34th year of operation, completed a 16-hour observation sequence of 3 Atlas in optical wavelength. What it saw shouldn't have been possible. Cometary tales obey a simple rule. They point away from the sun. This is not a tendency. It's a consequence of radiation pressure. As sunlight strikes dust particles in a comet's coma, photons transfer momentum, pushing the material outward in a long sweeping tail that always, without exception, extends in the anti-solar direction. It's one of the most reliable visual phenomena in astronomy. You can predict a comet's tail orientation with the same confidence you predict the sunrise. 3I Atlas broke that rule. For 41 minutes, between 08:14 and 08:55 UTC, the tail oriented itself at an oblique angle to the solar wind, approximately 34 degrees off axis. Then, gradually it realigned. The images were processed at the Space Telescope Science Institute in Baltimore, reviewed by 3 separate teams, and cross-referenced against starfield data to confirm the object's orientation. There was no instrument error, no calibration drift. The tail had moved. Dr. Laurie Fiega, a planetary scientist at the University of Maryland who specializes in cometary dynamics, was granted early access to the data under a rapid response observation protocol. Her analysis was brief and unambiguous. The observed tail morphology is inconsistent with passive outgassing or solar radiation pressure as the sole dynamic driver. Duration and angular deviation suggest an active transient force component. In plain terms, something pushed it. Let's walk through the physics. A comet's tail forms when solar heating vaporizes volatile ices, water, carbon monoxide, methane, on the nucleus surface. The gas expands outward, carrying dust particles with it. Sunlight then exerts pressure on those particles, accelerating them away from the sun. The result is a tail that streams behind the comet like the wake of a boat. For the tail to point away from the sun, the force of radiation pressure must exceed any lateral momentum from the outgassing itself. And it does, in every observed case, because radiation pressure is constant and unidirectional, unless something else is applying force. The three conventional explanations are rotational jet outgassing. If a comet has an active vent on its nucleus that's firing laterally as it rotates, the jet can create a temporary asymmetry in the coma. But this effect is transient, seconds to minutes, and requires high-velocity gas release. Spectroscopic data from 3I Atlas showed no corresponding surge in emission lines during the tail deviation. No gas, no jet. Magnetic interaction. If the comet's coma is sufficiently ionized, it can interact with the interplanetary magnetic field, creating a magnetic tail that can deviate from the dust tail's direction. But this requires a dense ionized component, and 3 Atlas's plasma density, measured by the Solar Dynamics Observatory, was 2 orders of magnitude too low. Nucleus fragmentation. If the comet's nucleus splits, the sudden release of internal pressure can create a burst of lateral momentum. But fragmentation events are visible as brightness increases and coma expansion. Hubble observed neither. So what's left? Dr. Fieger's report included a footnote buried in the technical appendix. If non-gravitational, non-radiative forces are excluded, the observed tail morphology would require an internal, directional impulse lasting 30-50 minutes. No natural cometary process matches this profile. She's careful. She doesn't say thrust. She says directional impulse. But the implication is the same. Something inside 3I Atlas, something that didn't vent gas, didn't fragment, and didn't interact with external magnetic fields, exerted force for 41 minutes in a direction inconsistent with solar radiation pressure, and then it stopped. There's a term in aerospace engineering for this: momentum dumping. It's what satellites do when their reaction wheels, internal flywheels used for attitude control, become saturated with angular momentum. To prevent unwanted rotation, the satellite briefly fires thrusters to release the built-up momentum into space, stabilizing its orientation. It's controlled, directional, transient. And from the outside, if you were watching a satellite dump momentum, you'd see exactly what Hubble saw: a brief deviation in expected force balance, followed by a return to equilibrium. But 3I Atlas is not a satellite. It's a comet, or it's supposed to be. The images circulated quietly. No press release was issued. Hubble's observation logs are public, but they're dense, hundreds of gigabytes of raw FITS files, accessible only to researchers who know where to look and how to process them. A few did. And in those circles, a conversation began. A planetary scientist at Caltech, speaking to a colleague on background. Comments later shared in a private Slack channel and subsequently leaked, put it this way: I can model 9 ways this could be natural, I just can't make any of them fit the timeline. 9 models, none adequate, and still no official statement from NASA or ESA acknowledging the anomaly. Because here's the problem. If you publish a paper saying we observed cometary tail behavior inconsistent with known physics, you're inviting scrutiny, speculation, and the possibility that you've missed something obvious. But if you don't publish, you're withholding data from an object that's already exhibiting unexplained radio emissions. So the data sits, processed, analyzed, logged. And on October 3rd, as 3 Atlas continued its slow approach toward perihelion, its tail, however briefly, bent in a direction comets do not bend. The universe had offered another clue, and the silence around it grew heavier. Chapter 4, October 8th, 2024. NASA held a press conference. The subject: organic molecules detected in Martian regolith by the Sherlock instrument aboard the Perseverance rover. For a brief moment, the world's attention turned away from 3i Atlas and toward Mars, toward the possibility that life, in some ancient microbial form, had once existed on the surface of another world. The discovery was not life, it was chemistry, but it was the kind of chemistry that whispers at the edges of biology. Sherlock's scanning habitable environments with Raman and luminescence for organics and chemicals is a spectrometer mounted on Perseverance's robotic arm. It uses ultraviolet laser pulses to excite molecules in rock samples, causing them to fluoresce in distinct patterns that reveal their chemical structure. On September 29th, during an analysis of a sedimentary rock sample designated Berea, Sherlock detected theophanies, benzene rings, and long-chain aliphatic hydrocarbons, organic compounds that, on Earth, are often associated with biological processes. Theophanies are sulfur-containing molecules found in crude oil and coal. Benzene is a simple aromatic hydrocarbon, a building block of more complex organic chemistry. Aliphatic chains, linear strings of carbon atoms, are the structural backbone of fats and waxes. None of these molecules are proof of life. They can form through abiotic processes, volcanic outgassing, meteorite delivery, Fischer-Tropsch reactions in hydrothermal systems. But their presence in sedimentary rock that formed in the presence of water, suggests an environment where the chemical preconditions for life existed. Dr. Abigail Allwood, the principal investigator for Sherlock, was measured in her language. What we've found is consistent with biological processes. It's also consistent with non-biological processes. The challenge now is determining which pathway produced these molecules, and whether that pathway was active when Mars had surface water. Translation: we don't know, but we're looking. The timing's eerie. 2 potential signals in 1 month, one from an interstellar object broadcasting at the hydrogen line, one from a planet where life might once have taken root. This is not the first time organic molecules have been detected on Mars. The Curiosity rover found them in 2018. But the molecules detected by Sherlock are more complex. Longer carbon chains, more functional groups, higher molecular weights. They're the kind of chemistry that, on Earth, sits just 1 step away from amino acids and nucleotides. The press conference was careful, optimistic, but guarded. Scientists spoke in conditionals, hedging every statement with could be and consistent with. There was no dramatic claim, no "we found life" headline. And yet, beneath the cautious language, there was a palpable sense of convergence. Because here's the pattern. For decades, the instruments we've sent into space, Hubble, Kepler, TESS, Perseverance, James Webb, have been searching for signs of life in distant atmospheres, on rocky planets, in the ice of ocean moons, and for decades the results have been incremental. A hint of water vapour here, a phosphine anomaly there, a methane fluctuation that might be geological or might be biological. But now, in October 2024, 2 instruments, separated by millions of kilometres, have detected phenomena that sit at the boundary of what we expected to find. One is chemical, one is electromagnetic. Neither is definitive, but both are anomalous. Is it coincidence, or is it instrumentation? Decades of technology development finally reaching the sensitivity threshold required to detect what's always been there, waiting for us to build eyes sharp enough to see it. Dr. Sarah Seeger, an astrophysicist at MIT who specializes in biosignatures, was asked this question in a post-conference interview. Her response was striking. "We've been building better tools for 50 years. It's possible we're not seeing more anomalies. We're just finally able to detect the ones that have always existed." That's the optimistic reading. The other reading is darker. We're in a moment of convergence not because the universe is suddenly revealing itself, but because we're finally looking in the right places at the right time. And what we're seeing is forcing us to expand the boundaries of what we thought was possible. On Earth, the discovery of organic molecules in Martian rock would be a headline for weeks. But in October 2024, it was a footnote. Because while scientists celebrated the possibility of ancient microbial life on Mars, an object broadcasting on the hydrogen line was drifting closer to perihelion, its trajectory bending, its tail misbehaving, its isotopic signature matching no known stellar environment. 2 signals, 1 month, and the questions multiplying faster than the answers. The press conference ended. the data was archived, and on Mars in the rust-red dust of Jezero crater, complex carbon molecules continued their silent testimony to processes we do not yet understand. Chapter 5, October 12, 2024. The European Southern Observatory released a spectroscopic analysis of 3I Atlas's coma composition. Water ice, carbon monoxide, hydrogen cyanide, all expected, all consistent with cometary volatiles. And then, in the deuterium to hydrogen ratio, an anomaly so stark it demanded remeasurement. Deuterium is heavy hydrogen, a hydrogen atom with a neutron in its nucleus. It's rare, comprising only 0.0156% of hydrogen in Earth's oceans, but its abundance varies depending on where and when it formed. Deuterium is produced in the Big Bang, enriched in certain stellar environments, and depleted in others. By measuring the DH ratio in a comet's ice, astronomers can trace its formation environment, its stellar nursery, its birth conditions, the molecular cloud from which it condensed. Oort cloud comets have a DH ratio of roughly 2 to 3 times Earth's ocean water. Kuiper belt objects have ratios closer to 1.5 times. Jupiter family comets, which formed closer to the Sun, have ratios near 1.0 times. 3I Atlas has a ratio of 4.2 times Earth's ocean water, 40% higher than any known comet. That's not a measurement error. It was confirmed by 2 independent spectrographs, the UVIS instrument at ESO's Very Large Telescope in Chile and the HIAS spectrograph at the Keck Observatory in Hawaii. Both found the same result. Dr. Olivier Hainaut, an astronomer at ESO who led the analysis, published a brief technical note in the Astronomers Telegram. The abstract was 3 sentences. Deuterium enrichment in 3I Atlas exceeds all previously measured solar system comets by a factor of 1.4. DH ratio is inconsistent with Oort cloud, Kuiper belt, or Jupiter family formation models. Origin environment remains unidentified. Let's unpack what this means. Deuterium abundance is determined by the temperature and density of the molecular cloud where an object forms. Colder clouds, farther from stars, less irradiated, preserve more deuterium because the reactions that destroy it are slower at low temperatures. Warmer clouds deplete deuterium faster. The Oort cloud, a reservoir of comets at the outer edge of our solar system, formed in a relatively warm region, close to the protosun, before being gravitationally scattered outward. Its comets carry a DH signature that reflects that warm formation zone. Interstellar space, by contrast, is colder. Molecular clouds between stars have lower temperatures and higher deuterium retention. If 3I Atlas formed in an interstellar molecular cloud, its DH ratio would be higher than solar system comets, and it is, significantly. But here's the problem. It's too high. Astronomers have mapped the DH ratios of molecular clouds across the galaxy using observations of deuterated molecules, DCO+, HDO, D2CO, in star-forming regions. 17 interstellar regions have been chemically characterized with sufficient precision to establish a baseline. 3I Atlas doesn't match any of them. Its DH ratio is 30 to 50% higher than the highest interstellar value measured, which means either it formed in a molecular cloud colder and denser than any we've surveyed, possible but unlikely, or its isotopic composition was altered by a process we don't recognize. There's a third option, rarely spoken aloud but present in every discussion. It didn't form in our galaxy's molecular clouds. Epsilon Eridani, the star toward which 3I Atlas's trajectory traces back, lies 10.5 light-years away in the constellation Eridanus. It's a K-type main sequence, star, younger and slightly cooler than the Sun, with a confirmed debris disk and possible planetary system. If 3I Atlas originated from a molecular cloud in the Epsilon Eridani stellar neighborhood, a region with different metallicity, different stellar winds, different radiation environments, its isotopic fingerprint would not match our solar system's comets. It would be alien in the most literal sense, formed in a different chemical context. But that raises another question. If 3I Atlas is extrasolar, why does it have a coma at all? Cometary comas form when solar heating vaporizes surface ices. But 3I Atlas, at its current distance from the Sun, is receiving only a fraction of the solar flux that typically triggers significant outgassing. Most Oort cloud comets don't develop visible comas until they're inside 3 AU. 3I Atlas began outgassing at 6 AU, twice the distance. That means either its ices are unusually volatile, sublimating at lower temperatures than water or CO, or something else is providing energy. Internal heat is one possibility, radioactive decay, tidal friction, chemical reactions, but none of these are sufficient to explain sustained outgassing over the timescales observed. There's a more speculative hypothesis. The coma isn't outgassing, it's venting. A vent implies directionality, control, the release of material from a specific location for a specific reason, cooling, pressure relief, momentum adjustment. It's the difference between a melting ice cube and a steam valve, and if the coma is a vent, then the deuterium anomaly takes on new significance. Because the isotopic composition we're measuring isn't the object's bulk chemistry, it's whatever material is being released. And if that material is being selectively vented, if it's not a passive response to solar heating but an active process, then we're not looking at a comet. We're looking at something else. Dr. Haynott's technical note ended with a single-line recommendation: follow-up high-resolution spectroscopy, required to constrain coma source region and outgassing dynamics. The recommendation was not acted upon. No follow-up observations were scheduled, and on October 12th, as the isotope data circulated through academic circles, 3I Atlas continued its approach, its coma glowing faintly in the infrared, its deuterium-rich ice sublimating into space from a place we cannot identify through a process we do not understand. Chapter 6, October 15th, 2024. A Freedom of Information Act. Request filed by a journalist at The Atlantic revealed something unexpected. 4 separate research teams had applied for James Webb Space Telescope observation time for 3I Atlas in September. All were denied. The James Webb Space Telescope is the most powerful infrared observatory ever built. Its 6.5-meter segmented mirror and suite of spectrographs can detect the faintest chemical signatures in planetary atmospheres, resolve the composition of exoplanet clouds, and peer into the dusty hearts of distant galaxies. It is precisely the instrument you would use to study an anomalous interstellar object with an unexplained coma, and it's not being pointed at 3I Atlas. The FOIA request uncovered the observation proposals submitted by teams at Harvard, the University of Arizona, ESO, and a consortium led by researchers at the SETI Institute. Each proposed different observation strategies: infrared spectroscopy of the coma, thermal mapping of the nucleus, detection of trace volatiles like methanol and formaldehyde, and high-resolution imaging to search for structural asymmetries. This stated reason for denial, according to the Space Telescope Science Institute's allocation committee, was uniform across all 4 proposals: schedule conflicts with Cycle 2 priorities. Cycle 2 refers to the second year of Webb's operational science program, a carefully curated list of observations selected through a competitive peer review process years in advance. These observations are high priority, scientifically valuable, and time-sensitive in the sense that their targets, distant galaxies, transiting exoplanets, gravitationally lensed quasars, are only visible at specific times. But here's the tension. Webb has discretionary time allocated for directors' discretionary programs, unexpected transient events, targets of opportunity, phenomena that couldn't be planned years in advance. In October 2024, Webb logged 14 hours of discretionary observations. 6 hours were spent on a gravitational lensing candidate in Able 2744. 4 hours on atmospheric characterization of WASP 107b, a hot Neptune. 3 hours on a supernova remnant in the Small Magellanic Cloud. All scientifically valuable, none time-critical in the sense that they're disappearing in 2 weeks. 3I Atlas is, and it received 0 observation hours. Why? The official answer is a resource allocation. Webb is booked, every hour is planned. Changing the schedule requires reprogramming slew paths, recalibrating instruments, and displacing other observations. It's bureaucratically complex. But there's another reading, one that circulates in private conversations among astronomers who've worked with high-profile instruments. Caution. Because if Webb observes 3I Atlas and finds something, if the infrared signature shows thermal emission inconsistent with passive solar heating, or if the spectroscopy reveals molecular species that don't match any cometary model, then the data becomes public. Webb's archive is open access. Within 12 months, every observation is released to the global research community. And if that data is anomalous, the questions escalate. Press coverage intensifies, speculation multiplies, and the institution managing the telescope, NASA, STRSCCI, the consortium of international partners, becomes the focal point of scrutiny. It's easier to not look. Dr. Jane Rigby, the chief scientist for Webb operations, was asked about the denied proposals during a stakeholder meeting in Baltimore. Her response was brief. "We prioritize observations based on scientific merit and feasibility. The proposals for 3i Atlas were competitive, but they did not meet the threshold for displacing scheduled Cycle 2 programs. Translation: we made a choice. Science over opportunity." But what if the opportunity is the science? Because here's the unspoken tension. Webb was designed to observe the distant, the faint, the ancient. It was built to see the first galaxies, the atmospheres of potentially habitable worlds, the chemical signatures of star formation in epochs when the universe was young. It was not designed for interstellar objects. There's no protocol for rapid response observations of transient phenomena in our own solar system. But it could be. The instrument is capable. The time exists. What's missing is institutional will. And so, on October 15th, as the most powerful infrared telescope in human history continued its slow survey of the distant cosmos, an object exhibiting unexplained radio emissions, trajectory deviations, isotopic anomalies, and tail dynamics drifted through the inner solar system, unexamined by the very instrument that could resolve its chemistry. The data we could have is not the data we're collecting, and the silence around that choice is louder than any explanation offered. Chapter 7, October 18th, 2024. A routine mapping pass by the Mars Reconnaissance Orbiter's HiRISE camera captured something unexpected on the surface of Phobos, a linear feature, 12 meters long, straight, fresh, and in a region that 8 months prior had been photographed with no such feature present. Phobos is Mars's largest moon, a small, irregularly shaped body just 22 kilometers across, heavily cratered, tidally locked, and slowly spiraling inward toward eventual destruction in the Martian atmosphere. It's been imaged thousands of times, its surface is mapped in exhaustive detail. And now, there's a line where there wasn't one before. HiRISE, the high-resolution imaging science experiment, is the most powerful camera ever sent to another planet. It can resolve features as small as 30 centimeters from orbit. When pointed at Phobos, it can detect boulders, crater chains, and the grooves that stripe the moon's surface like scars. The new feature appears in image PSP 3479010, captured during orbital pass 2347 on October 18th. It's located in Phobos's sub-Mars hemisphere, the side that permanently faces Mars, at coordinates 8.3 Degren, 157.2 Degree W. It's straight. That's the first anomaly. Impact ejector rays are radial, branching outward from a central crater. Tectonic fractures on small bodies are irregular, following stress lines in the crust. Sublimation channels, cracks formed by escaping subsurface ice, are sinuous, shaped by the path of least resistance. This feature is straight, edge-defined, and oriented at a precise 42-degree angle to the moon's equator. The second anomaly: there's no crater overlap. When a fresh impact occurs, it obliterates or partially buries older surface features. This line crosses two ancient craters without disturbance, meaning it formed after those craters, recently enough that subsequent impacts haven't erased it. The third anomaly: it's in a region photographed in February 2024, orbital pass 24193, where no such feature existed. 8 months. And something changed. Dr. Alfred McEwen, the principal investigator for HiRISE at the University of Arizona, reviewed the images personally. His analysis was logged in the mission's internal documentation and later leaked via academic channels. Feature morphology is inconsistent with impact ejector, tectonic fracture, or sublimation channel. Timing suggests formation within the last 8 months. Mechanism unknown. Recommend re-imaging. The recommendation was approved. A second pass was scheduled for November 4th. But before the follow-up image could be captured, the story leaked. A JPL engineer, identity protected, shared the finding with a colleague, who posted a comparison image on a private Discord server dedicated to planetary science. Within hours, it was on Reddit. By evening, it was trending on Twitter. NASA issued no statement. So what is it? The conventional explanations are limited. Phobos is a geologically dead body. It has no atmosphere, no tectonics, No volcanic activity. It's a rubble pile, a loose aggregate of rock held together by its own weak gravity. But it does have one dynamic process: tidal stress. As Phobos orbits Mars, the planet's gravity exerts tidal forces that flex and compress the Moon's interior. Over millions of years, this stress could create fractures, but those fractures would be irregular, not linear, and they wouldn't appear suddenly. There's a more speculative explanation: impact ejecta from Mars. If a meteorite strikes the Martian surface with sufficient force, it can eject material into orbit. Some of that material intersects Phobos's path and impacts the Moon at high velocity, creating linear features where the ejecta strikes at shallow angles. But this requires precise geometry. The ejecta must travel hundreds of kilometers, intersect Phobos's orbit, and strike at an angle shallow enough to create a line rather than a crater. It's possible, but the odds of it happening in an 8-month window in a region previously imaged are remote. The third explanation is one no one wants to articulate publicly: something moved. There's a long history of speculation about Phobos. Its low density, 1 png-cm3, barely more than water ice, suggests it's not solid rock but a porous, fractured interior. In the 1960s, Soviet astrophysicist Yosif Shklovsky proposed, half seriously, that Phobos might be hollow, a natural satellite with an artificial interior. The idea was dismissed. Phobos's orbital dynamics, cratering history, and spectroscopic signature are all consistent with a captured asteroid. There's no evidence of artificiality, but there's also no clear evidence explaining a 12-meter linear feature that appeared in 8 months. On October 18th, the image was archived. The follow-up observation was scheduled, and a JPL engineer, speaking off the record to a reporter from New Scientist, offered a single line that captures the disquiet. It's probably nothing, but we should image it again before we say anything publicly. Translation: we don't know, and until we do, we're silent. The pattern is familiar. An anomaly detected. Data logged. Follow-up planned. And while the scientific process unfolds at its careful, methodical pace, the observation window narrows, the geometry shifts, and the opportunity to understand what we're seeing slips further away. October 2024 was starting to feel like a month when things that shouldn't move were moving. Chapter 8, October 21st, 2024. Dr. Davide Farnocchia, a navigation engineer at NASA's Jet Propulsion Laboratory, published a revised ephemeris for 3 Atlas. An ephemeris is a table of predicted positions, where an object will be at a given time, based on its orbit and the gravitational forces acting on it. For planets and asteroids, ephemerides are extraordinarily precise. For comets, they're less so, because comets don't obey pure Keplerian orbits. They experience non-gravitational forces, outgassing jets that push the nucleus off course, a phenomenon called the rocket effect. 3I Atlas was experiencing non-gravitational acceleration, but there was no rocket effect. The revised ephemeris showed a cumulative trajectory deviation of 0.041 degrees since August, an angular shift that, projected to perihelion, translates to approximately 700 kilometers. That's not subtle. That's a measurable sustained deflection, requiring continuous force over weeks. For a typical comet, this would be unremarkable. Outgassing thrust is well documented. When sunlight heats a comet's surface, ice sublimes into gas, which escapes into space, exerting a tiny jet of thrust. If the outgassing is asymmetric, stronger on one side due to rotation or surface composition, the comet gets nudged off its gravitational trajectory. The effect is small, but over months it accumulates, and it's predictable. You can model the thrust based on the comet's brightness, its spectroscopic signature, its rotation rate, and the solar flux it receives. Dr. Farnocchia tried, and the model didn't work. 3I Atlas's spectroscopic signature, measured by the UVs and Hires instruments, showed water, CO, and HCN emission, typical cometary volatiles. But the emission rates were too low by a factor of 3 to account for the observed trajectory deviation. In other words, the comet was being pushed, but not enough gas was escaping to do the pushing. Farnocchia's paper, submitted to the Astronomical Journal, included a footnote that would, under normal circumstances, be a footnote. But given the accumulating anomalies, it became something else. non-gravitational acceleration. Source remains unidentified. Let's walk through the numbers. The observed trajectory deviation implies a cumulative velocity change, delta v, of approximately 0.12 meters per second over 70 days. That's tiny. A gentle nudge, but it's sustained, directional, and consistent. To achieve that delta v through outgassing, the comet would need to eject roughly 8,000 kilograms of gas and dust per day in a preferred direction. Based on the observed brightness and spectroscopic emission rates, 3I Atlas is ejecting roughly 2,500 kilograms per day. The missing 5,500 kilograms per day is the problem. You can't push a comet without expelling mass. Newton's third law is unambiguous. Every action has an equal and opposite reaction. If the comet is accelerating, something is being ejected. If nothing is being ejected at the required rate, then the acceleration shouldn't exist, but it does. There are three possible explanations. 1. The outgassing is dark. Some comets eject large amounts of dust without producing visible gas emission. The dust carries momentum, but it doesn't show up in spectroscopy because it doesn't emit light. It only reflects it, faintly. If 3I Atlas is ejecting dark, fine-grained dust in large quantities, the missing thrust could be hiding in material we're not detecting. The problem? Hubble's images show no significant dust production. The coma is faint, diffuse, and optically thin. There's no evidence of a massive dust component. 2. The outgassing is intermittent. If the comet is venting in short, intense bursts rather than continuous steady-state outgassing, the average emission rate could be low while still producing significant thrust during active periods. The problem? Continuous monitoring by the Swift satellite and ground-based photometry shows no large brightness fluctuations. The comet is stable, not episodic. 3. The acceleration isn't outgassing, which leaves what? Solar-wind interaction is too weak. At 3I Atlas's distance, solar wind pressure can produce accelerations on the order of 10·7 ms2. The observed acceleration is 10·4 ms2, 3 orders of magnitude higher. Tidal forces from the Sun or Jupiter are negligible. The comet is too far, too small, and on the wrong trajectory for tidal torque to matter. Magnetic interaction requires a dense plasma coma and a strong interplanetary magnetic field. 3I Atlas has neither. So what's left? Internal force, something generating thrust from within the object without producing visible exhaust. That's where the language becomes uncomfortable, because internal force without exhaust is not a natural cometary process, it's propulsion. Dr. Farnocchia is careful. He doesn't speculate beyond the data. His paper presents the observations, the models, and the discrepancy. But in the conclusion he writes, the nature of the non-gravitational force remains an open question. Future observations at higher cadence and spectral resolution may constrain the mechanism. Translation: we don't know what's pushing it. And the silence around that admission is profound, because in 70 years of cometary observation, we've modelled thousands of non-gravitational accelerations. We understand the physics. The equations work, until now. A colleague of Farnocchia's, an anonymous source quoted in a Nature news brief, put it more bluntly. If this were any other comet, we'd have an explanation by now. The fact that we don't means either we're missing something obvious, or the comet is doing something comets don't do. On October 21st, the revised ephemeris was published. The trajectory deviation was documented, and 3I Atlas continued its approach toward perihelion, accelerating in a direction we could measure but could not explain. This was the chapter where "we don't know" became louder than "we know." Chapter 9, October 24, 2024. A brief press release from the China National Space Administration appeared on the state-run Xinhua news agency Wire. The subject: Queqiao 3, a communications relay satellite designed to support China's Chang'e lunar exploration program, specifically missions to the far side of the Moon, where direct Earth communication is impossible. The release was routine: technical specifications, orbital parameters, mission timeline. But buried in the fourth paragraph was a single line that caught the attention of international observers. Queqiao 3 has been tasked with auxiliary observation of anomalous interstellar object 3I Atlas, using its UHF backup array. No elaboration, no context, no follow-up. It was the first time a national space agency had publicly acknowledged 3I Atlas as anomalous in an official capacity. Queqiao-3 is not an astronomical observatory. It's a relay satellite, a communications hub positioned at the Earth-Moon L2 Lagrange point, where it can maintain constant line of sight with both Earth and the far side of the Moon. Its primary instrument is a 4.2-meter parabolic antenna for high-bandwidth data relay. Its secondary payload is a UHF radio array, lower frequency, lower bandwidth, designed as a backup in case the primary system fails. It's not designed to observe comets, but it's equipped with a radio receiver capable of detecting signals in the 400-500 MHz range, which includes harmonics of the hydrogen line at 1.42 GHz. Why would China retask a lunar relay satellite to observe 3i Atlas? The answer is not in the press release, but it's in the timing. October 24th is 8 days after Hubble captured the backward-bending tail, 10 days after the ESO-deuterium anomaly was published, 5 days after the unpublished third radio signal was detected and leaked, and 3 days after Dr. Farnokia's trajectory paper was submitted for peer review. China, like every space-capable nation, monitors the International Astronomical Union's circulars. They have access to the same observation logs, the same spectroscopic data, the same trajectory models, and they have their own assets. The Queqiao-3 retasking suggests they've calculated something, some parameter, some probability, some risk assessment, that warranted redirecting a mission-critical satellite toward an object that, officially, no one is particularly concerned about. Dr. Andrew Jones, a journalist specializing in Chinese space activities, noted the oddity in a tweet. Queqiao-3's UHF array is backup comms gear, not science payload. Retasking it means CNSA either expects a signal or wants plausible deniability for observing one. Either way, interesting. Plausible deniability. That's the phrase that resonates. Because if you're a space agency and you want to monitor an object that might be emitting anomalous radio signals, you don't announce it as a primary mission. You don't publish observation schedules. You don't invite scrutiny. You retask an existing asset quietly under the cover of operational flexibility, and you log whatever you detect internally. And if something happens, if the object emits another signal, if the pattern continues, if the evidence becomes undeniable, you have data. Private data. Data that no other agency has, because they chose not to look. It's strategic, and it's revealing. Because it suggests that China's space program is treating 3i Atlas not as a curiosity, but as a priority. Which raises the question, what have they seen or calculated that prompted this decision? There's a geopolitical dimension here. Space science is collaborative, but it's also competitive. The first nation to confirm an anomalous signal, especially one with potential implications for non-natural origin, gains a strategic information advantage. Not militarily, scientifically. And in the 21st century, scientific authority translates to soft power. China's lunar program is ambitious. Sample return missions, a lunar research station, crewed landings planned for the 2030s. But those missions require infrastructure, relay satellites, navigation networks, communication protocols. Queqiao-3 is part of that infrastructure, and now it's also monitoring 3i Atlas. The press release was translated into English by multiple news outlets, most focused on the lunar mission aspects, the far-side landing sites, the rover deployments. Only a few noted the 3i Atlas mention, and none could explain why a lunar relay satellite was being used to observe an interstellar object. NASA, when asked for comment by a Space News reporter, offered a single-sentence response. We're aware of the announcement and continue to monitor 3i Atlas through our existing observational assets. Translation: no comment. The European Space Agency said nothing, and so, on October 24th, the world learned that one of the 3 major spacefaring nations had decided that 3 Atlas warranted retasking a lunar satellite, an operational asset with mission-critical responsibilities, to observe it. Why? The answer wasn't in the press release, it was in the silence that followed. Chapter 10, October 27th, 2024. So 3.14 UTC, 3i Atlas reached perihelion, its closest approach to the Sun, at a distance of 0.61 astronomical units, approximately 91 million kilometers, slightly closer than Venus, and at that moment it became visible, not to professional observatories, not to Hubble or the VLA or ESO's massive arrays, but to amateur astronomers with backyard telescopes 8-inch reflectors, equatorial mounts, CCD cameras across the northern hemisphere. For the next 11 days, until November 7th, 3i Atlas would remain bright enough, magnitude 10.2, to be detected by anyone with the right equipment, clear skies, and the patience to find it. This is the chapter where the story shifts, where it stops being something that happens in institutional silences and starts being something anyone can participate in. Because if something happens, if the coma brightens, if the tail shifts again, if there's an outburst or fragmentation event, it will likely be documented first not by NASA, but by a citizen scientist in their driveway in Colorado, or a retiree in rural England, or a high school astronomy club in New Zealand. History has precedent. On October 24, 2007, an amateur astronomer named Juan Antonio Enriquez Santana was observing Comet 17P Holmes from the Canary Islands when he noticed something extraordinary. The comet had brightened by a factor of 400,000 in less than 24 hours. A magnitude 17 object, invisible to all but large telescopes, had become visible to the naked eye at magnitude 2.8. He reported it. Within hours, observatories worldwide confirmed the outburst. Holmes had undergone a catastrophic fragmentation event, releasing megatons of dust and gas into space, creating a coma larger than the Sun. Professional astronomers missed it. An amateur caught it. The reason is simple. There are more amateur telescopes pointed at the sky on any given night than professional ones. The amateurs have flexibility. They can change targets on a whim, follow hunches, revisit objects that look interesting. Professionals operate on scheduled programs, peer-reviewed proposals, allocation committees. If 3i Atlas does something unexpected, the people most likely to see it are not scientists. They're hobbyists. So here's how to find it. On October 27th, 3i Atlas is located in the constellation Virgo, approximately 8 degrees south of the bright star Spica. Its right ascension is 13H, fortbouillon towards 18s. Its declination is 16 degrees is 22 30. It's moving slowly, about 0.4 degrees per day, eastward across the ecliptic. At magnitude 10.2, it's too faint for binoculars but easily visible in an 8-inch telescope under dark skies. It will appear as a faint greenish smudge, the coma, with a possible faint tail extending to the west. The green colour comes from diatomic carbon, C2, emission, a common cometary signature. To photograph it, you'll need a telescope with at least 6 inches of aperture, a tracking equatorial mount to compensate for Earth's rotation, a CCD or CMOS camera with sensitivity in the visible and near-infrared, 30-60 second exposures stacked to reduce noise. Processing the images is straightforward. Subtract dark frames, flat field to remove vignetting, stack multiple exposures to increase signal to noise, and then enhance the contrast to bring out faint structures in the coma and tail. What should you look for? Brightness changes. If the coma suddenly brightens or dims, log the time and magnitude. Tail morphology. If the tail shifts direction, becomes asymmetric or develops streamers, document it. Outbursts. If the coma expands rapidly or develops concentric shells, capture as many frames as possible. Color shifts. If the coma changes from green to blue or red, note the timing and duration, and then report it. The International Astronomical Union's Central Bureau for Astronomical Telegrams accepts reports from amateur astronomers. So does the American Association of Variable Star Observers. So does the Comet Observation Database maintained by the Minor Planet Center. Your data matters, not because professional observatories can't observe 3i Atlas. They can, but because they're not observing it continuously. And in the gaps between scheduled observations, transient events can occur and vanish without record. The Holmes outburst lasted 6 days before fading. If no one had been watching that night, we'd have missed it. The brightness would have decayed, the coma would have dispersed, and the only evidence would be a faint dust trail detected months later with no understanding of what caused it. 3i's Atlas is here, visible, accessible, and for 11 days the story is no longer being written exclusively by institutions. It's being written by anyone willing to look. On October 27th, as the sun dipped below the horizon across the northern hemisphere, hundreds of amateur astronomers pointed their telescopes toward Virgo. They captured images, they logged magnitudes, they measured positions, and they watched, with a mixture of curiosity and unease, as a faint greenish coma drifted slowly eastward against the stars, an object that had travelled for millennia across the interstellar void, broadcasting on the hydrogen line, bending its tail against solar wind, accelerating without gas, carrying isotopes from a stellar environment we cannot identify. It was there. And for once, seeing it didn't require a billion-dollar telescope or a PhD. It required a telescope, a clear night, and the willingness to look up. Chapter 11. October 30th, 2024. 04:33 UTC. The Parkes Observatory in Australia detected a second radio burst from 3I Atlas. Duration 22 seconds. Frequency 1.42 GHz. Signal-to-noise ratio 8.4. It was not an instrumental artifact. It was not ionospheric interference. It was a coherent emission, frequency stable, originating from the same point source that had broadcast on September 14th. The detection was confirmed by Dr. Emily Petroff, a radio astronomer at the Australian National University specialising in fast radio bursts. Her team logged the event, cross-referenced it with satellite telemetry to rule out terrestrial sources, and submitted a technical note to the Astronomers Telegram within 6 hours. But the story didn't end there, because buried in the engineering logs, released later through academic backchannels after a data-sharing agreement between Parkes and ALMA, was a reference to a third event. October 19th, 2011 UTC. Duration 9 seconds. Frequency 1.42 GHz. It was detected, logged, and never published. Why? The October 19th signal was faint, signal-to-noise ratio of 4.2, just above the detection threshold. In isolation, it would have been classified as marginal, not robust enough to warrant publication without confirmation. So the observatory flagged it internally, scheduled follow-up observations, and waited. The follow-up came on October 30th, and this time the signal was strong. 3 signals, same frequency, same source. September 14th, 38 seconds, October 19th, 9 seconds, October 30th, 22 seconds. The intervals between them are key. September 14th to October 19th, 35 days. October 19th to October 30th, 11 days. The interval is shortening. This is the pattern that transforms data into narrative. Because if the signals were random, solar wind interactions, ionospheric glitches, cosmic ray bursts, they wouldn't exhibit temporal structure. Random events are Poisson distributed. No pattern, no memory, no rhythm. But 3 events with shortening intervals is not random. It's sequential, and sequences imply causality. Dr. Petroff's technical note included a single-line observation. Temporal spacing suggests non-random emission pattern. Further monitoring warranted. Translation: this is not noise. This is structure. The question no one was asking publicly, but everyone was thinking privately, is what happens next? If the pattern continues, the next signal should occur approximately 7-8 days after October 30th. That places it between November 6th and 7th, right at the edge of the amateur observation window. But there's another pattern embedded in the data: the signal durations. 38 seconds, 9 seconds, 22 seconds. If you plot them chronologically, there's no obvious progression. But if you plot them by cumulative energy, the total number of photons emitted, integrated over duration and signal strength, the pattern becomes clearer. The first signal was the strongest, the second was the weakest, the third was intermediate. Why? One possibility: the source is rotating, and we're seeing a lighthouse effect. If 3I Atlas is emitting a directional beam, a focused radio pulse, and it's rotating, then the strength of the signal we detect depends on how closely the beam aligns with Earth during emission. When the beam points directly at us, we see a strong signal. When it's off-axis, we see a weak one. But that requires the source to be artificial. Lighthouses are built. Pulsars, natural rotating emitters, produce periodic signals, the same duration, the same interval like clockwork. 3I Atlas's signals are not periodic, they're episodic, and the intervals are changing. The other possibility: the signals are intentional, not periodic, not random, intentional. And if they're intentional, then the shortening intervals might be adaptive, a response to proximity, a countdown. This is the line of reasoning no one articulates in peer-reviewed journals. but it's the line of reasoning that circulates in private emails, in conference back channels, in late-night conversations among researchers who have spent years listening to the cosmos and hearing nothing. Because if you were designing a signal, a beacon, a probe, a communication protocol, you would want it to intensify as you approached your target. You'd want the intervals to shorten, the frequency to remain constant, the pattern to be unmistakable. You'd want whoever was listening to notice, and we noticed. A Reddit thread appeared within hours of the park's announcement. User Astrometry Nerd posted a simple scatter plot, 3 points, with dates on the x-axis and signal duration on the y-axis. The title of the post: "If this pattern holds, the next signal is in 7 days. Who's watching on Novi 6?" The post received 14,000 upvotes, hundreds of comments, amateur astronomers shared coordinates, radio enthusiasts discussed software-defined radio setups. Someone posted a Python script for automated signal detection. The scientific community was silent. The public was mobilizing. Because here's the tension. Institutions move slowly. Papers take months to publish. Proposals take years to fund. But the observation window is 11 days. And if the pattern holds, if there's a fourth signal on November 6th or 7th, it will coincide with the last night 3i Atlas is visible to amateur telescopes. The geometry is closing, the window is narrowing, and the question everyone is avoiding is the one that sits at the center of the pattern. What happens if there's a fourth signal? And what happens if there isn't? Because both outcomes are unsettling. If there's a fourth signal, the pattern is real. And if the pattern is real, then the object is not behaving like a comet. It's behaving like something that's aware of time, distance, and geometry. If there's no fourth signal, then the first three were, what? Coincidence? Instrumental errors? A statistical fluke with odds so long they feel like intention? On October 30th, as the second confirmed signal circulated through academic networks and amateur forums, a single line appeared in a private Slack channel used by SETI researchers. The message was from a senior scientist, name redacted, who had spent 30 years listening to the cosmos. It read, "I don't know what this is, but I know what it looks like." No one replied. Chapter 12. November 2nd, 2024. NASA announced the final payload selection for Dragonfly, the rotorcraft mission to Titan, Saturn's largest moon, scheduled for launch in 2028. It's a marvel of engineering. A dual quadcopter drone equipped with mass spectrometers, seismographs and cameras designed to fly through Titan's thick atmosphere, hopping between methane lakes and organic-rich dunes, sampling the chemistry of a world where prebiotic molecules rain from the sky. Dragonfly will launch in 2028. It will arrive at Titan in 2034, and for the next decade, it will explore one of the most promising environments in the solar system for understanding the origins of life. It's inspiring, it's ambitious, and it's also a reminder of the mismatch between our capability and our timeline. Because while Dragonfly is being built to explore a moon that might harbour the chemistry of life, an object exhibiting potential signs of non-natural origin is passing through our solar system right now, and we're sending nothing. Let's talk about what we could be building. A rapid interstellar interceptor is not science fiction. The technology exists, the infrastructure exists. What's missing is priority. Here's the mission architecture. 1. Launch vehicle, Starship, fully reusable, capable of delivering 100 tons to low Earth orbit. Cost per launch, approximately $10 million once fully operational. 2. Propulsion, a solar electric or nuclear electric propulsion stage. Ion drives are mature technology. NASA's Dawn mission used them successfully for over a decade. Thrust is low, but it's continuous, and over months it accumulates to high delta V. 3. Payload, a lightweight probe, 500 kilograms, equipped with a high-resolution camera similar to HiRISE, a near-infrared spectrometer similar to Webb's NIRSpec miniaturized, a magnetometer, a radio transceiver capable of detecting emissions in the 1-2 GHz range, a dust analyzer similar to Cassini's cosmic dust analyzer. 4. Flight time, approximately 18 months to intercept 3i Atlas at current velocity and trajectory, achievable with a departure window in late November 2024 using a Jupiter gravity assist. Cost $400 $600 million, less than a single James Webb instrument, a fraction of the Mars Sample Return Program. But it's not being built. Why? The answer is risk. A rapid response interstellar interceptor has no guaranteed science return. If 3I Atlas is just a comet, anomalous, yes, but natural, then the mission is wasted in the eyes of budget committees. The data would be valuable, but it wouldn't revolutionize our understanding of comets in the way that, say, the Rosetta mission did. But if 3I Atlas is not just a comet, if it's something else, then the mission is not wasted. It's historic. It's the moment we stop speculating and start knowing. The problem is, we don't know until we go. And going costs money. And money requires justification. And justification requires consensus. And consensus requires time. And time is what we don't have. Compare this to Dragonfly. Titan is not going anywhere. It will be there in 2034, and in 2044, and in 2054. The science is patient. The timeline is flexible. 3 Atlas will be gone in 6 weeks, and it will not return for 80,000 years. This is the mismatch. We're optimized for long-duration, high-certainty missions. We're not optimized for transient, high-uncertainty opportunities. But the universe doesn't care about our optimization. It delivers phenomena on its own schedule. And if we're not ready to respond, if our infrastructure is too slow, our budget's too rigid, our institutions too cautious, then we miss the opportunity. Dr. Alan Stern, principal investigator for the New Horizons mission to Pluto, has advocated for years for a rapid response capability in planetary science, a pre-approved budget and spacecraft design that can be activated on short notice when an unexpected target appears. In a 2019 interview, he said, "We missed Oumuamua because we weren't ready. We'll miss the next one too if we don't build the infrastructure now. It's not a question of if another interstellar object will arrive. It's when, and whether we'll be prepared. We weren't prepared for Oumuamua. We're not prepared for 3I Atlas. And unless something changes, we won't be prepared for the next one either, because the technology is ready. Starship is flying. Ion drives are proven. Miniaturized instruments are mature. The bottleneck is not engineering. It's institutional inertia. And so, on November 2nd, as NASA celebrated the Dragonfly payload selection, a mission that will explore prebiotic chemistry on a distant moon a decade from now, an object exhibiting radio emissions, trajectory deviations, isotopic anomalies, and temporal signal patterns continued its passage through the inner solar system, unvisited by anything more sophisticated than a radio dish. We have the tools. We have the talent. We have the infrastructure. What we don't have is the will to use them on a timescale that matches the opportunity. Chapter 13, November 5th, 2024. A team of astronomers at UC Santa Cruz published a preprint, not yet peer-reviewed, but rigorously calculated, showing something that made the 3I Atlas anomalies feel less like a collection of coincidences and more like a pattern. When you trace 3I Atlas's trajectory backward, unwinding its orbit through the gravitational influence of the Sun, Jupiter, and the interstellar medium, its incoming vector aligns within 0.8 degrees of Epsilon Eridani, a K-type star, 10.5 light-years away, slightly cooler and younger than the Sun, and one of the closest stellar systems with a confirmed debris disk and possible planets. The alignment is not proof of origin. Space is vast. Trajectories can point anywhere, and 0.8 degrees, while narrow, is not 0. But Epsilon Eridani is not arbitrary. It's been a SETI target since 1960, when Frank Drake pointed the Green Bank radio telescope at it during Project Ozma, the first systematic search for extraterrestrial intelligence. It's young enough to still have planetary formation, activity, close enough to be reachable within a human lifetime using current propulsion concepts, and now an object with unexplained radio emissions, trajectory deviations, and isotopic signatures inconsistent with our solar system is arriving from its direction. The UC Santa Cruz team, led by Dr. Ruth Murray Clay, an astrophysicist specializing in exoplanet dynamics, calculated the trajectory using astrometric data from Pan-STARRS, the VLA and Gaia. The analysis accounted for solar gravity, galactic tidal forces, and proper motion of Epsilon Eridani itself over the 300,000 years it would take an object to travel 10.5 light-years at 31 km/s, Their conclusion: 3 Atlas's incoming trajectory, when corrected for galactic motion and gravitational perturbations, is consistent with an origin in the Epsilon Eridani system within observational uncertainty. Probability of random alignment, approximately 1 in 20,000. 1 in 20,000. Let's unpack that. There are roughly 200 billion stars in the Milky Way. At any given moment, if interstellar objects are being ejected randomly from stellar systems, their trajectories should point in random directions. The chance that one would align within 1 degree with a specific nearby star is vanishingly small, but it's not zero. And this is where the interpretation splits. The skeptic's position: 1 in 20,000 odds happen. Low probability events occur all the time if you observe enough events, and we've only observed a handful of interstellar objects: Oumuamua, Borisov, 3 Atlas. It's entirely plausible that 3I Atlas originated from a completely different stellar system, and the Epsilon Eridani alignment is coincidental. The alternative position: 1 in 20,000 odds are suspicious when combined with other anomalies. If 3I Atlas were a normal comet, no radio signals, no trajectory deviations, no isotopic mismatches, then the alignment would be interesting but not compelling. But when you stack the anomalies, each individually explainable but collectively improbable, the coincidence becomes harder to dismiss. Dr. Murray Clay's paper includes a statistical framework called Bayesian inference, which calculates the probability of different hypotheses given the observed data. Without going into the math, the conclusion is straightforward. If you assume 3I Atlas is a natural comet, the combined probability of all observed anomalies, radio signal, trajectory deviation, isotope ratio, Epsilon Eridani alignment, is approximately 1 in 8 million. If you assume 3I Atlas is artificial, the observed anomalies are consistent with expected behavior. She's not claiming it's artificial, she's saying the data fit the hypothesis better than the natural one, and that's the line no one wants to cross publicly. Because once you say, the artificial hypothesis fits better, you're inviting a cascade of scrutiny, skepticism, and the potential reputational damage of being wrong. But the data are the data. Epsilon Eridani is 10.5, light years away. If 3I Atlas originated there and travelled at its current velocity, 31 kilometers, the journey would take 107,000 years. That's a long time. Long enough that any civilization capable of launching interstellar probes would need to think in generational timescales. Long enough that the probe would need to be autonomous, no real-time control, no mission updates, just pre-programmed instructions and adaptive decision-making. Or, if the object is not a probe but a derelict, something launched long ago and now adrift, it could simply be following a ballistic trajectory, its original purpose forgotten, its systems degraded, its emissions the faint echoes of technology that once functioned. We don't know, but the alignment is there, and the odds are steep. On November 5th, as the preprint circulated through academic networks, the responses were polarized. Some researchers dismissed it outright. Trajectories are uncertain. 0.8 degrees is not a precise alignment. Epsilon Eridani is one of hundreds of stars within 20 light-years. This is confirmation bias. Others took it seriously. The alignment is narrow enough to warrant follow-up. If we can refine the trajectory with more astrometry, we can constrain the origin. If it tightens, that's significant. If it widens, it's coincidence. And a few, quietly, in private conversations, acknowledged what no one wanted to say publicly. If I were designing an interstellar probe and wanted to visit Sol, I'd launch it from the nearest sun-like star. Epsilon Eridani fits that criterion. The paper ended with a recommendation. Continued astrometric monitoring of 3 Atlas is essential to refine trajectory constraints and assess the statistical significance of the Epsilon Eridani alignment. The recommendation was not acted upon. No additional astrometry campaigns were funded, and on November 5th, as 3T Atlas drifted deeper into the southern celestial hemisphere, dimming below magnitude 11, the window for precise trajectory measurement began to close. The alignment was there, the odds were calculated, and the question remained: coincidence or convergence? Chapter 14, November 7th, 2024. Tonight is the last night 3I Atlas will be visible to amateur telescopes across the northern hemisphere. After this, it dims below magnitude 12. It becomes a target only for professional arrays, large apertures, long exposures, precise tracking. And most of those arrays are not pointed at it. This is the chapter where documentation meets reflection. Where the accumulation of data, the pattern of anomalies, and the institutional silence converge into a single uncomfortable question. What do we do when the universe offers us something we don't understand, and we choose not to look? Let's summarize what we know. September 14th. 3 independent observatories detect a coherent 38-second radio emission from 3I Atlas at 142 GHz, the hydrogen line. The signal is logged, verified, and then not publicly discussed for 2 weeks. October the 1st. SpaceX demonstrates full booster recovery with Starship Flight 5, proving the capability to launch rapid response interstellar missions. No such mission is planned for 3I Atlas. October 3rd. Hubble captures 3I Atlas with a cometary tail oriented against the solar wind for 41 minutes, behavior inconsistent with passive radiation pressure. No natural cometary process fits the timeline. October 8th. Perseverance detects complex organic molecules in Martian regolith, potential biosignatures, though not definitive. 2 anomalies in 1 month. October 12th. Spectroscopic analysis reveals a deuterium to hydrogen ratio 40% higher than any known comet, inconsistent with solar system or mapped interstellar formation environments. October 15th. A FOIA request reveals that 4 research teams applied for James Webb observation time for 3I Atlas. All were denied. Webb has logged 14 hours of discretionary time in October on other targets. October 18th. The Mars Reconnaissance. Orbiter photographs a fresh 12-meter linear feature on Phobos. Straight, edge-defined, in a region imaged 8 months prior where nothing existed. October 21st. Dr. Finocchia publishes a revised ephemeris showing a cumulative trajectory deviation of 7,200 kilometers, with no corresponding spectroscopic evidence of outgassing thrust. The acceleration source remains unidentified. October 24th. China's space agency announces that the Queqiao 3 lunar relay satellite has been tasked with observing 3I Atlas, publicly acknowledging it as anomalous. October 27th. 3I Atlas reaches perihelion. For 11 days it's visible to amateur astronomers. Citizen scientists begin monitoring. October 30th. A second radio signal is detected. 22 seconds, 1.42 GHz. Engineering logs reveal a third unpublished signal on October 19th. 3 signals, shortening intervals, 35 days, then 11 days. November 2nd. NASA announces Dragonfly's payload, a mission that will arrive at Titan in 2034. No rapid response mission to 3I Atlas is funded or planned. November 5th. Trajectory analysis shows 3I Atlas's incoming vector aligns within 0.8 degrees of Epsilon Eridani, a K-type star 10.5 light-years away with a debris disk. Probability of random alignment, 1 in 20,000. 14 pieces of evidence, none definitive, all anomalous. If you take any one in isolation, there's a conventional explanation. Comets emit radio noise, trajectories deviate, isotopes vary, tails fluctuate, alignments happen. But when you stack them, when you consider the cumulative improbability, the conventional explanations strain, and the silence grows heavier. Because here's what hasn't happened. No follow-up radio monitoring campaign, no James Webb observation, no rapid response mission, no public NASA statement addressing the anomalies, no coordinated international observation effort. The data are public, the instruments are capable, the object is here, and the response is cautious inaction. Why? Part of it is institutional risk aversion. If you investigate an anomaly and find a conventional explanation, you've wasted resources. If you investigate and find something extraordinary, you've invited scrutiny, skepticism, and the burden of proof. Part of it is the reputational cost of being wrong. Science is built on reproducibility and peer consensus. Announcing, "We found something anomalous," before exhausting every natural explanation is professionally risky, and part of it is the sheer strangeness of the possibility. Because if 3I Atlas is not natural, if it's artificial, if it's technological, if it's evidence of extraterrestrial engineering, then the implications are so profound they dwarf every other scientific question, and institutions don't move quickly when the stakes are that high. But the observation window doesn't care about institutional timelines. It closes tonight. So here's the call. If you have a telescope, 8 inches or larger, and clear skies, point it at 3i Atlas tonight. The coordinates are right ascension 13 52 44's, declination 19 +12 18, magnitude 11.8. It's faint. You'll need dark skies, a tracking mount, and patience, but it's there. Photograph it. Log the time, measure the brightness, note any changes in the coma or tail, and report your observations to the Minor Planet Center, the AEVSO, or the IAU's Central Bureau. Your data matters. Because the professional observatories, the ones with the budgets, the instruments, the institutional authority, are not watching continuously. And in the gaps between their scheduled observations, transient events can occur and disappear without record. If something happens tonight, an outburst, a brightness change, a tail anomaly, the person most likely to document it is not a NASA scientist. It's someone in their backyard, with a telescope and a camera looking up. And if nothing happens, if 3i Atlas fades quietly into the southern sky, dimming, receding, becoming just another entry in the catalogue of interstellar visitors, then we'll be left with the data we've already collected and the questions it raises. Because here's the uncomfortable truth. We don't know what 3i Atlas is. We know what it's not. It's not a typical comet. It's not behaving like Oumuamua or Borisov. It's not matching the models. But we don't know what it is, and the window to find out is closing. On November 7th, as the sun set across the northern hemisphere, astronomers, professional and amateur, pointed their instruments toward Virgo. They captured photons that had travelled millions of kilometres from a small icy nucleus drifting through the inner solar system. Some saw a comet, others saw a question. And all of them, whether they articulated it or not, were confronting the same tension that sits at the heart of scientific inquiry, the gap between what we observe and what we understand. Because science is not about certainty, it's about asking better questions, and 3 Atlas, in its strange, silent way, is asking us a question we're not ready to answer. What do we do when the data stops fitting the models? Tonight, we watch. Tomorrow, the window closes. And after that, all we'll have are the images, the measurements, and the knowledge that for a brief moment, the universe offered us something extraordinary, and we let it leave. We are standing at the edge of the known, staring into a signal we don't yet understand. There is a kind of silence that forms in the space between observation and understanding. It's not the absence of sound. It's the weight of questions we don't yet have the language to ask. Questions that sit at the edges of instrumentation, at the limits of peer review, in the uncomfortable territory where data meets doubt. 3i Atlas is gone now. Not vanished. Its position is calculable. Its trajectory known, but beyond reach. Dimming, receding. Returning to the interstellar medium from which it came, carrying with it the unanswered questions it delivered. The hydrogen line signal, the backward-bending tail, the deuterium anomaly, the trajectory deviation without gas, the shortening signal intervals, the alignment with Epsilon Eridani. None of these are proof, but all of them are evidence. Evidence that something about this object does not fit the comfortable categories we've built to organize the cosmos. And the silence around that evidence, the institutional caution, the denied observation proposals, the absence of follow-up, is its own kind of answer. It tells us that we are not ready. Not ready to confront the possibility that the universe might be more active, more intentional, more populated than we've allowed ourselves to imagine. Because the implications are vast. If 3i Atlas is artificial, if it's technological, if it's evidence of engineering from a stellar system 10.5 light-years away, then the cosmos is not a passive stage. It's a network, a web of civilizations, probes, signals, and intentions stretching across distances we've only just begun to measure. And if it's not artificial, if every anomaly has a natural explanation we haven't yet found, then we've learned something equally profound, that nature is stranger, more varied, more inventive than our models predict. That comets can bend tails, emit radio bursts, and carry isotopic signatures from molecular clouds we've never surveyed. Either way, the universe is teaching us, but we have to be willing to listen. On November 7th, The observation window closed, but the data remain. The images, the spectra, the radiologs, the trajectory models, they're archived, accessible, waiting for someone with the patience and the tools to look deeper. And maybe that's the real story. Not the object itself, but our response to it. The way we choose to investigate, or not investigate, the phenomena that challenge our assumptions, because the universe will deliver more visitors, more anomalies, more signals that sit just outside the boundaries of the known, and when they arrive, we'll face the same choice: look, or look away. For now, 3i Atlas is drifting southward, below the ecliptic, beyond the reach of amateur telescopes. But it's still out there, still moving, still carrying whatever it carries: ice, dust, deuterium, and the faint electromagnetic whisper of something we heard 3 times and could not explain. And somewhere, in the cold vastness between stars, the light of Epsilon Eridani continues to shine, a distant beacon 10.5 light-years away where perhaps something else is watching, waiting, listening,